And here with me, we have my name's Song, and I've been application scientist. Steve Raba was the service engineer, and he's a genius, repair things. XQ was the technical manager, and he also technically very strong. Gerald Carter, application scientist, he lives in Germany, and Louis Pachenko, who is
Austria, Song, Austria.
Okay.
Yeah, yeah.
I'm American. My geographic knowledge is very limited. Anyways, and Louis Pachenko, who's a former application engineer in France, and he also formed the company. It's called the CS Instrument, which is something amazing. And our goal here is to basically keep supporting our people and then keep the instrument live for the next 10 years. And hopefully we could have some good results for everybody. And we're here to provide training and lecturings, and it's a weekly. So I will not talk too much about anything for too long. And we want to make it as a slightly not official. And then you're welcome to ask questions, because among the audience, we have quite a few of former employees, engineers of Agile Technologies, and then all of us can help you. And we hope you together this place to seek your help. And if you happen to have other old instruments like, VCOs, Bookers, multi-mode, we're happy to help too. Okay, and let's see, physics and AFM, atomic force microscope, number 4, why contact mode is great. So there's a misconcept, and I was just putting out a post in LinkedIn last night, and I was like, oh, what should I put it in? Look at the webinars provided by other companies, other great corporations. They're also the latest, the greatest, how many channels, high bandwidth, modes, 300 different imaging modes. And I ask myself, look at your best image. What imaging modes do you do? Oh, the best image is actually not a lot of very complicated modes. There's sometimes just contact mode. And then and I just say, oh yeah, contact mode, that's a good topic, because I would suggest, make a point that atomic force microscope is a difficult instrument to master, and the image that comes out highly depends on your skill and your understanding. It's almost like the relationship between camera and your picture, and then your piano and your music. And you can have the greatest piano in the world, and then you may still a very bad musician, and you could be the best musician and have a very bad piano, and it does not prevent you from a best musician. So and I try to say, you don't need the expensive FM. If you know what you're doing, you don't need it. You can have great things happen to your existing old instrument. Okay. Touch base a little bit, recoup a little bit the thing we've done. The Agilent 5500 is a tip scan instrument and tip scanning. And then let's see, where's it joining? Okay. And then let's see, go forward. And this is the design of the scanner, as you can see. How do I make it move? So this scanner is a pendulum structure, and then here the two knobs on the top are laser alignment. And here's how do you scan the thing. It's not working very well. And then the laser shine on the back of the cantilever and bounce it back. And then the this is scan, now it scans. So the whole thing scans like a swings. And then you adjust these two knobs to adjust the laser, so it points to the back of the cantilever. And then the laser bounce back to this point, and then we put a detector to detect the laser point. Okay, I want you to keep that picture in your mind, so when you adjust things, you know what is it you're adjusting and what kind of things you're aligning. That's what basically it is. Okay, so contact mode. This is a basic force curve of a contact mode. The tip and sample will approach each other at a zero force between each other, and then as they are getting very close, there's an attractive force, and then they turn into a pulsive force. If you pull the tip away from the sample, it's going to pull back and then snap back into zero force. There's an adhesion force here. Okay, the working point or set point is always a point on this tilted line where the feedback will maintain the tip to sample height. So the force of the measured force is matching this set point. The force curve on the left is the force curve when you measure it when it's in air. The one on the right is when you do the force curve in liquid. Okay, why did it look different? That's because in air, there's adhesion force and there's some condensations on the surface of the sample. So when tipping is hit the sample, it always been sucked into the sample because of this capillary force. So you have adhesion force. When it's in liquid, the liquid is everywhere, and therefore these adhesion capillary force is no longer in effect, and therefore the adhesion force pull up force is no longer there. Why should I tell you that? That is because it tells you when you're imaging in air, because of the adhesion force or capillary force, the tipping sample is always sucked into each other with a strong repulsive force. So contact mode in air does not give you high resolution on soft samples, and that's a known factor. But however, if you put this in liquid, not just water, liquid, including water, organic solvent, so on and so forth, you could actually carefully position your set point, make it extremely close to 0 point. When you manipulate that, you can have a very, very small amount of force. And then when you do that, you minimize your sample distortion and protect your sharpness of your tip. As simple as that, nothing else. Contact mode. Okay. Contact mode, how does it work? Again, I rephrase that, is that you have a scanner scan over the tip, and then you have the force going up and down. And if you maintain a constant force, the scanner will move up and down, trace a profile, and this profile mimics the topography of the sample, and that is your image. That's one way of imaging. You could also, by scanning over the surface with very low feedback or minimal feedback, basically you just scan the whole tip over the sample. What happened is that your topography image turns flat, but your deflection mimics the topography. And we call this constant high mode. And why do I say that? Because when you do constant high mode, there's no feedback there. Your feedback is no longer part of the loop, and therefore you could scan the sample really, really fast. There's no accurate Z measurement because either your Z no longer work, but your deflection signal just looks like a topography, and then you can scan real fast. Why do you want to scan real fast? That's because when you scan real fast, you can capture in situ imaging, like dissolving or something. You can capture it because in that case, you need to scan fast because you have chemical reaction happening. So that's kind of like a cheap way to achieve high speed scanning without extra $200,000. Here, I'm going to show you a bunch of examples of data, and all of them are obtained with contact mode. And this is a living cell. I think it's a endothelial cell, and then we can see the cytoskeleton. The reason we use contact mode because tapping mode will agitate the cell, and the cell will leave the attachment to the sample. Sometimes it doesn't work, and then contact mode actually works pretty well. And remember this one thing: try not to use a very sharp tip. You have to blunt your tip before you scan a living cell. And here's another endothelial cell, and then this cell is alive. You can see that. You can see that the some materials is ejected from the membrane, and the cell is actually exchanging material with its environment. This is also a self-exam monolayer image that was contact mode, where you control force. The resolution is very, very high. This scan size is only 400 nanometers. And here's another 400 nanometer scan of a self-exam monolayer of thiol on surface of gold. You can see an array of molecules, very high resolution. It's all done with contact mode. When you do tapping mode, it's actually, I never seen a good resolution image of self-exam monolayer with tapping mode. Okay, another thing that great is with contact mode is that you could, in contact mode, it's much easier to manipulate your force. Very easy. And not a tapping mode, I have to spend 5 minutes to explain what is a set point in tapping mode, and then chances are most people still ask me what is the set point. But in contact mode, set point is force. You increase the set point, you increase the force. And here I scan this self-design model and I increase the force and scan small size. I remove part of it. Basically, I cause a scratch. And then I scan larger area with a low set point. So it's very easy to change from imaging to scratching by just manipulating force. Force is very simple. And if you reduce the set point until tip samples start to leave each other, that's your force is 0. You increase the set point until tip sample barely engage, that force is very, very small. And these are atomic lattice image on a self-design monolayer using contact mode. You can have a very precise and atomic resolution, atomic lattice type of image. And I'm not going to go details, and I'm trying to keep my presentation not to be too long, so we can have enough time to talk to each other. So this is basically constant height mode of this calcite on the surface scan, and on the left image is constant force mode, just like everybody does with high feedback. The one below is constant height mode. We can scan 15 lines per second. When I push it, it can scan all the way to 40 lines per second. The following are using contact mode to image a chemical reaction in real time. We need to scan a bit fast. So we choose a very soft tip, and then this is high resolution image of a self-assembly as it happens. That's time 0, 3.5 minutes, 6 minutes, 8 minutes, and so on and so forth. Contact mode totally capable of imaging something at very high resolution. This is image, I just add this image this morning. I was preparing a poster last night for a LinkedIn post, and I want to show something that's very good looking, but also very simple. And I try to make a point that you actually don't need a very expensive instrument to get high resolution image, because it's just like play your music instrument. You need to know the music. Here, how do we get this amazing atomic steps of silicon surface, and then the image is very clean? And if you do tapping mode, image will not be this clean. The reason is simple. No matter how careful you are, your sample is gonna accumulate some pollutions, contaminations from the air. No matter how careful you are, it's always there. I mean, you could be very careful. Now, when you do tapping mode, because tapping mode, the force is really soft, so any contaminations on the sample is gonna show up on your image, and then there's no way around it, right? But when you do contact mode, it's very simple. You just increase your set point, just increase it. When you increase the set point, you're actually wiping away any pollutions, contaminations there. And then if you can do this in, this image is collected of the silicon sample in IPO, isopropanol alcohol, okay? So you wipe away these contamination, where you wipe it away and dissolve into your solution, and you get very good resolution. And this is one of my demo data. When I say demo data, is when people show up with a sample and they get their result. Every time is within 1 or 2 hours. So we don't have time to re-prepare the sample. And all we did is put them isopropanol, imaging in liquid, and then increase the force set point, so the contamination will wipe it out. Simple. Okay, so say thank you for these partners, and this nanocube technologies is my invention. I have lots of liquid cells that invented. Well, you can see them on this website. ZoomAFM.com is our gathering point. Hopefully I will keep this app every week. Honkyo Service was a business by Steve Rabat, and he was the best repair guy. And the CSI instrument was the company formed by Louis Pachenko, former employee of Agent Technology. They did something amazing. They actually built add functions to their controller. They can actually control your existing AFM, including your Agilent and your vehicle, and they have their own AFM too, if you're interested, and drop a mail to me. Thank you for your time. I can use some questions right now. Yeah, you can unmute yourself and then ask me questions.
Hi, Song. Thank you for your presentation. I was just wanting to know, why do you need to blunt your AFM tip before you image live cells? Is it to reduce puncturing?
Yes, that's correct. Not only cells, but also, how do I say this? For example, lipid bilayer, lipid membranes. And even when you do tapping mode, or sometimes you do Mac mode, reduce your sharpness of the tip will help you to have a better image, because the lipid bilayers, the membranes, those that when you have very sharp tip go into your sample, it does not stop by your sample. Yes.
I see. Thank you.
Okay, you guys go ahead and unmute and ask me questions. At the same time, I'm going to point my camera to my AFM. I will show you how to align the laser without your optical microscope. Right, put this here. I have this instrument right in front of me. Okay, it's connected. This is the AFM. And then here my scanner is already there. Oh, by the way, before I do that, I'll show you what a proper way of install your cantilever. Let me change to a different camera. I just installed this multiple and camera system. I can actually show you different views of different things. Here it is. Okay, so this is a camera that shows the cantilever, and then have a light here. No, it's a scanner on surface, and I have a optical microscope point to very close to it. Let me switch to a different view. You can see very, very close to it. Here we go. Okay, so this is a yes, okay. So this is another high magnification optical microscope, and then you can see the tip is installed there. It's kind of hard to see the tip. Here I have one tweezer on the left, another tweezer on the right, and this is the 5500 scanner with its nose cone, and this golden chip is the cantilever. And then here there are tips there, but it's kind of hard to see because of the dark background. And that's the proper way of install your cantilever. People keep asking me, how much you should put into it. The proper way is to have two things. One is the wire should be about 30% into the chip, okay? And then the cantilever, which is right here, should be inside this window, because you need to have laser shine on top of that and bounce it back to your windows. So 30%, sometimes 25% works, 50% is a little bit too much. That's because imagine that you need to have this tip to contact the sample before the wire. See, there's a wire here. This wire also has a certain thickness. This cantilever chip is tilted down about several degrees, I think 10 to 12 degrees, I forgot. But you have to have enough of this length of this chip that is tilted down, so the wire does not touch the sample before the cantilever tip touches. So yes, today I'm not very prepared because the tip is already there, and then I lost this little key to open the wire. So I'm just going to show you the correct way, and then I'm going to move my camera to the instrument. I show you how to align the laser without your optical microscope. Let me switch the camera. Okay, let's see if I can hold my hands here. Okay, so a little shaky, so I'm going to put my hands down. All right, so you have this scanner on top, and then you look below it. You need to remove the sample, because when the sample is there, your laser is blocked by the sample. You have to remove the sample. So let me put it down. Okay. Next, make sure you turn the laser spot on. Turn it on. Okay. And then you look at these instrument cell. You can see that there is a bright spot underneath it. That's a laser spot. Okay. If you don't see the laser spot, if you actually don't see it, that means that laser spot may be blocked by something. Okay. So what you do is that you look at this knob. There are two knobs on top. Oops. Two knobs on top. One on the left, one on the back. The one on the back move the laser up and down. So you turn this one counterclockwise. When you turn it counterclockwise, you move the laser spot slightly into the empty space. Now, before I move forward, see if I can. Oh, here it is. See if I can draw this. Okay, see if I can draw it with one hand. So imagine the imagine there's a imaginary circle, which is the view of the your optics, and then this is the optics, and you have this cantilever is right here, the chip is right here, okay, and here is your tip, okay. So here is the laser spot. You need to move this to here, okay. First, you move this up and down until you see this edge. So when you see this edge, this laser spot will disappear right here, okay? Once you get here, you move backwards, so it'll reappear. Don't move backwards too much, move a little bit, reappear, and then you move left and right until you see a scatter. When you see the scatter, that tells you that your laser is blocked by something. If you don't see the scatter, there's a chance your cantilever is no longer there. You broke it. Okay, so I'm going to put this thing there on the AFM and just do that. Okay, first of all, I move this knob up and down until the laser spot hit the edge. Okay, up and down. Now it disappears. And move back a little bit. All right, so now it's on the edge. And then you move left and right. How do you move left, right? Here, use the knob on the left. This one, move left and right. Okay, so just watch this laser spot, left and right. Now there's a scatter right here. There's a scatter. Take a look at it. See, that scatter even has a tilt angle when you flip this a little bit. So now you see a scatter. Let me show you again. No scatter, scatter. No scatter, scatter. Okay. Now, I want you to remove the detector. This is the detector. You have to remove it. Okay. So now watch here. No scatter, scatter. When scatter happens, if you look at the frosty glass, there's a laser spot start to show up. Okay. Let me move away. No laser spot. No laser spot. No laser spot. Spot. At that moment, you know your tip, your laser is on the cantilever. Okay. Right here. And because this cantilever is a like shape of two legs, so you move backwards until actually it's in the middle. And now you see the laser spot. That's where your laser is aligned. Okay, so I'm going to show you this operation and adjust the laser. Of course, the next step is that you have to flip your optical detector, flip it, and look at the position of the PSPD, the photo detector. And because this laser spot here is in the middle and slightly to the left, you have to adjust the knob so this also in the middle and slightly, because it's flipped, it's on the right. And then you push it in all the way until it stops. And then you adjust these two until on the computer screen, this red dot right here is at the proper place. Okay. And you're done for the adjustment of laser, and then you can put the sample back and you're ready to approach. Okay. Yep, I'm not going to go any further because that's involved to put the instrument online and then show you the entire operations and so on and so forth. And we probably were running out of time. Turn this on.
Hello?
Yes. If you have a question, unmute yourself and then ask. Yeah, go ahead.
I was the fellow who emailed you about the STM drift. And I was just wondering if you had any tips on making sure that the mount was level or that anything like that was off. I'm pretty new to STM, so I'm just trying to figure out how to make sure the sample's set up properly.
Which instrument do you have? What's the model?
We have the, let me see. It was the STM-A.
TMA. And then do you have the 5500 or other instruments?
Yeah, I think it's the 5500.
5500. Okay. So you have STM-A, and what is your sample?
It's just a gold 111.
Gold 111. Okay. You have gold and you have STM-A, and then how do you fix your sample on the sample holder?
We have that circular mount, and then we have kind of like two pins that hold it on either side.
Okay.
But I know that there's alternative methods like tape and whatnot. I'm wondering if maybe one of those is superior to this type of sample or something like that.
Yes. The biggest enemy of STM is drift. STM, essentially, the STM-A has 1 by 1 micron in XY range. I think it's about 2 to 250 nanometer in Z range. In other words, it has a very small range compared to AFM, right? The small AFM scanner is 10 micron XY, 500 nanometer to micron in Z, I forgot. And large scanner has 20 micron on Z. So you have 250 nanometer on Z. So the drift is the biggest problem. Every operation, every mount, you have to care about the drift itself. For example, if you put a sample glued on piece of chuck, and if the tape is not pushed all the way and there's a creep, little drift, that's huge amount of drift. So that's the biggest thing you're gonna facing is try to reduce as much soft contact and make sure that the sample is solidly on the surface and no drift. That's very important. That's one. Two is gold 111 is not a very good sample for you to start to work with. That's because gold sample, when you expose gold 111 in air, it gets contamination real fast. In about 30 minutes, your surface is full of junk. So if you want to practice and get the best parameter, you should try to use HOPG, not gold.
Okay. Thank you.
Sure.
Would you suggest another way to mount the sample so there's not as much drift besides tape or glue, perhaps?
Yes. You need to have as much tight in contact as possible. And how do I say this? If you have liquid cell, you can fix the sample down even with your liquid cell. This makes the whole thing extremely tight. And if you want to use tape, you basically push down very hard, or you could use thermal glue that's also very tight. You know, your drift is only as good as the mount, the material you use. And if you use polymer or rubbery or any kind of glue, it's as good as this, I'll tell you. And also one more drift, the source of drift is the how do I say this? The tip mount itself. So when you mount the tip, the tip you normally bend a little bit. When you bend this a little bit, this bending will gradually creep back. So try not to bend it too much, and that's also will reduce your drift. Try to show you this, but this become blurry now. I don't know. Probably the okay, background. So yes, the when you do STM, the biggest enemy you're fighting is drift. There you go. It's coming. I might have a couple of minutes because I just put on my AFM computer is also online. I can show some of the basic steps on the instrument itself, and you can actually see it operates. Give me a second. Host. Yes. Okay, so now I actually put the AFM computers online, and the AFM. I just align the laser, and then everything's ready to go. And then let me see, I can click. This is approach for people who's not familiar with 5500. This is approach button, and click that. Then you see approach in progress. That is the motor is clicking, moving forward until tip touches the sample. Okay, now it sees that the approach stopped, right? Next time, next thing you look at is this green bar. This is the Z range of the scanner. And if you see this yellow bar, that's height of the sample. This height of the sample is slightly higher than middle, and that means the approach seems to overdid a little bit. It's slightly over approached. Okay, so how do you move back? You can use your finger to move the knobs back a little bit, or you could use motor function here, and you turn one motor, rear, left or right, any one of these, and you click, in this case, open. Now it's in the middle. Basically, I step the sample away from the tip a little bit until it's in the middle. Okay, now the tip and sample is engaged, and my scan size here is 8 micron, and scan speed is 1.8. I can reduce 1.5, 256 line per 256 pixels. Okay, and then here is my servo. Look at the servo, 15%, which is good. P servo you can fix at 20%, not to have to move. This is the AFM small scanner with 2 micron Z range. As you can see, the AFM approached slightly higher than that. It's probably 200 nanometer higher than the middle. If it is STM, the tip is already probably crashed. So yes, AFM is much more forgiving. And then you click this button, which shows that it's scanned down. Click that. And then your image starts. At the beginning, the image is blurry. That's because your color table is from plus to minus micron, and your sample is only plus minus several hundred nanometers. So you need to click this A button. It automatically adjusts the color. And then you can manually adjust up and down. All right, while we are here, I'll show you a couple of parameters. This is IGAN. That basically tells you how sensitive, how fast you want the feedback to be. If this is too high, there will be noise, and if it's too low, it'll be blurry. Okay, I'm just going to show you when it's too low. Right now it's 15. We'll go to 1. That's too low, and then you can see that the topography become blurry, and your deflection looks like topography. That's exactly what I talked before. It's called constant height mode. You can go this one as low as 0.1. Just don't make it 0. Okay, 0.1. You can see the topography completely disappeared, and then your deflection signal looks like your topography. Right, almost like a topography. Only it's the Z is in millivolts. It's not accurate. Okay. This scan is not calibrated, so the image looks elongated, and then you can read these numbers and you can change your calibration. Calibration is right here. Scanner, and you change this number, and then you change calibration. This is obviously not calibrated. And change this number and make it different, right? Ideally, you do this carefully on the sample that is carefully turned orthogonal, and then get the correct readings. Okay, so now we are actually now we are scanning at this constant height with no topography image, and let's see how fast you can scan. This is 1.5 hertz. Let's increase to 5. And there's no quality change of the topography. Let's go to 10. You can easily scan 10 lines per second, real fast. So why do you want to do that? Because if you want to watch something happen in real time, you want to scan fast. And that's a good way to do that, is to rely on the constant height imaging mode. Where now the tip is not responding up and down topography on the Z feedback, but just rely on the deflection signal, force signal, to collect this topography image. Let me go the other way, this constant height, and I can always increase my gain. It's 15 again. Now my topography start to show up. It's still blurry. Let me go to 20. How about 30? Yeah, now you see your topography image become more and more clear. 50. 60. Now you scan pretty fast, and your topography image is reasonable. And another way to say that is that when you have high gain, you can scan faster and maintain reasonable image quality. And why do you want to scan fast? Some of the work you want to do in situ, you want to capture the moment of imaging, and scan fast has its advantage. Okay, next I'm going to mimic some kind of problems, and anybody in the audience can tell me what's going on. What did I do? I just observe what's happening. Okay, why it disappeared? What happened is that I just manually withdraw the sample. So sample is too far away now. You can see the yellow line get extended to a point that it's outside of the range. Okay, this happens when there's a drift in the sample, and then it can drift closer or too close or too far. Either way, image will disappear. Okay, so I think this is what time is now? Yes, we're quickly running out of time. I'm going to stop the scan and do a withdraw. And back to my presentation here. Stop sharing. And feel free to ask questions. Otherwise, thank you for your time, and see you next week.